Observing collapses the wave function. We've all heard that. But still, back when I studied quantum mechanics, no one told me how observation is actually defined. Why does it collapse the wave function? What's the difference between observation and measurement? What do they actually mean in theory and in practice, in classical and in quantum physics? What is this about? Hi, I'm a theoretical physicist and this is Standard Quantum Mechanics and its measurement problem. When I got introduced to quantum mechanics, I learned about the Copenhagen interpretation. Like all interpretations of quantum mechanics, it's supposed to tell us what the math and rules of quantum mechanics actually mean, so what they tell us about the real world. It is the standard interpretation, or at least it used to be, mainly because it was the first one that was somehow widely accepted. And the Copenhagen interpretation tells us that observing the wave function collapses it, which means it goes from being in a weird quantum wavy superposition thing to one definite thing. So for example, from a wave function that describes a particle that could basically be everywhere, to a wave function that describes a particle which is here, because that's where we measured it. Of course, this raises a lot of questions, like why? Why does this happen? And if the answer is because of the observation, then we want to know what observation actually is and how it does this. So how does standard quantum mechanics, how does the Copenhagen interpretation of quantum mechanics define observation? Spoiler alert, it doesn't. Oh, we'll get there. But first, to understand why that's the case and what this means for us, we have to take a closer look at the words observation and measurement. What's the difference between observation and measurement? Is there even a difference between observation and measurement? If your answer is yes, then you're right, as long as you're talking about classical physics. If your answer is no, then you're right if you're talking about quantum mechanics. If you look at a ball on a ramp, you see it rolling down. So you make an observation. The observation that balls roll down. Now, if you measure the distance the ball rolled within a certain time, you make a measurement. The difference is that making a measurement, you attach a specific number to this situation. So in classical physics, observation answers questions like what is happening? And measurement attaches a number to this. It answers questions like how far does the ball roll down? So every measurement is a specific kind of observation. But not every observation is a measurement. Now, let's say the ball and the ramp are really small. No, I mean really small. So small that we can't see them, not even with a microscope. But for some reasons, we can find out the position of the ball at certain times. Since we can't see the ball, we don't know that it's rolling down. So how can we answer the question, what is happening? Well, to find out what's happening, we have to get the ball's positions. And then, knowing the positions, we can conclude that the ball indeed rolls down. But how do we get the positions? By measuring them. So if we want to know what's happening, we already have to make measurements, because the stuff we're talking about is just so tiny. And that's why in quantum mechanics, observation and measurement are basically the same thing. So I think we should stop using the word observation when we're talking about quantum mechanics, because it leads to the understandable misunderstanding that this is about a conscious human being. But most physicists agree that this is not the case. Consciousness plays no role in this whole measurement thing. The basic math of quantum mechanics does not relate measurement to consciousness. What does it say about measurement? Well, nothing. There is no mathematical operation within the basic framework of quantum mechanics that describes the process of measurement. There's no measurement function, no measurement operator. How is this possible? And if that's true, where does the statement measurement or observation collapses the wave function come from? If we don't even know what measurement is. Before I answer the first question, it would be wonderful if you could give this video a like. And if you're watching this on your phone, you can now hype my videos to support my small channel. Thanks for your high points and your likes. So, to answer the first question, in classical physics, measurement is a precisely defined process because it must fulfill certain conditions. For example, it must be repeatable. This means if you measure one thing and then you measure the exact same thing again, you must get the exact same value in the range of measurement precision. But in quantum mechanics, a measurement is certainly not repeatable. If you measure the spin of a particle, you may get spin up one time and spin down the other time. So you can't repeat your measurement. In quantum mechanics, measurement doesn't satisfy conditions, like it does in classical physics. This makes it incredibly hard, if not impossible, to define what measurement actually is. Okay, but then how can this be a thing? This is an attempt to preserve the completeness of quantum mechanics. What does that mean? So let's say we have a particle and we have a corresponding wave function describing it. Before we measure the particle, the wave function describes it as being in a superposition. But you know, if we measure it, we only get one certain outcome. For example, spin up. How can you solve this? One possibility is that the particle will spin up the entire time, we just didn't know. Then there's no collapse. Our math is just not complete. Our theory is not finished. That's not what Copenhagen says. Copenhagen says quantum mechanics is complete because it provides a full description of everything that is knowable about reality. This means we could use the rules of quantum mechanics to calculate everything we could possibly know. Maybe the required calculations are too complicated for us, but in principle we could figure out everything that can be known. There's nothing hidden from us. This is all we could possibly know right now. But if this is true and then suddenly this is true, if there's nothing hidden or missing, then we need a cut, a switch, a collapse to explain this. So Copenhagen needs the collapse of the wave function because it says our theory is complete and our measurement is correct. We only get one certain outcome. Copenhagen does not say why or how the collapse happens. Well, it says the collapse happens because we measure it. But this means we're in a circle. What's a measurement or observation? Something that triggers the wave function to collapse. What is the collapse of the wave function? It's what happens when you measure it. Yep. Again, the math of quantum mechanics gives you no equation that tells you when, why, or how a measurement happened. So the best answer I can give to the question, what is the collapse of the wave function, is the attempt of the Copenhagen interpretation to preserve the completeness of quantum mechanics. And the answer to how is a measurement or observation defined is standard quantum mechanics does not define what a measurement is. I know, this is not the answer you were hoping for, and we can do a bit better, as I'll show you in a moment. But first, this is why standard quantum mechanics has a measurement problem. And if you've ever been confused about the collapse of the wave function and the whole measurement thing, this is not your fault. The confusion is basically built into quantum mechanics. Your teachers didn't tell you what the collapse of the wave function actually is, because they didn't know. So this shows that Copenhagen is not enough, at least philosophically. Physicists didn't stop here. There are other interpretations of quantum mechanics that somehow define what measurement is more clearly. And there's something you could call a practical compromise. See, in reality, when we want to measure something quantum, we have to interact with it. You can shoot light, so photons, at an atom. The atom absorbs the photon, which gives the atom extra energy. To get rid of the energy, the atom emits another photon. This combination of absorbing and re-emitting light is how you could image atoms. Or you send charged particles through a cloud of molecules. These particles interact, charging the molecules, which then interact with vapor, so you can see it condense. And also electrons hitting a screen is nothing more but interaction. The incoming electron gives energy to the screen's atoms. When they get rid of their energy, they emit photons, so light again. And that's what you actually see. So you can say measurement is interaction. And other interpretations of quantum mechanics often use interaction to define measurement. GRW theory, for example, says that wave functions don't just only collapse if someone observes them, but they collapse on their own due to a precise physical threshold. So if there's enough interaction going on, if there's enough matter, the spontaneous collapse simply must happen. And that's a measurement. Interaction with enough matter. You probably know that many worlds does not require a collapse of the wave function. It requires something we call decoherence. It was long hoped that decoherence could solve the measurement problem. But decoherence cannot tell us why we measure spin up. But at least it can tell us why we measure spin up or spin down and nothing in between. It explains this using the interactions with the environment. I don't have time to go into this now, so I'll talk about this next week. But importantly, you can take away measurement is always about interaction. And quantum mechanics has confusion built into it, especially standard quantum mechanics. So if the whole observation measurement thing confuses you, you can join the rank of all physicists. Standard quantum mechanics does not define what a measurement actually is. And this question is still not solved. If you're wondering why there are so many interpretations, check out this video. Thanks for watching, have a wonderful day.